what you have the drop height. That's pretty much it. To measure the acceleration of the vulnerable device inside, which is a printed circuit board where the solder joints are located, is certainly a tremendous challenge. And to measure the displacements and velocities, it's certainly also a challenge. So there is an incentive to substitute drop tests with shock tests, but at the same time, you can do whatever you want, provided that you know what you do. By the way, many, many years ago, when I was a PhD student in Moscow University, I asked my advisor, Professor Lomakin, can I do this? Can I do that? Can I do this? And he said, look, you can do everything what you want, provided that you know what you're doing. So we want to know what we are doing, and that always helps. So a shock test is a specially designed and approximately tuned shock tester is employed in a short-term load of the given magnitude, say a constant or an half-sine load with a maximum value of 500 Gs. And duration, say, acting for 1 millisecond, is applied to the support structure of a component or device. There's an obvious incentive to compare the dynamic response of the given structural element to the shock and drop loading. So one wants to find out how a shock tester should be tuned in order to adequately mimic the drop test conditions. That's certainly an incentive. And here's what you see. On the left-hand side, you see drop testing situation. On the right-hand side, you see a shock testing situation. And the bottom line, there are also a lot of information, equations, solutions, analyses. But the bottom line is a shock test can adequately mimic drop test conditions if the drop test conditions are modeled and the shock tester is adequately tuned in terms of maximum induced acceleration, duration of loading, and if necessary, the shape of the impulse in accordance with the predicted drop conditions. In other words, modeling comes first. You want to model drop tests for the given height, drop height. You want to model shock tests. You want to compare them and the results. And in this case, it will not be apples and oranges. It will be apples and apples in terms that, let's say, the criterion is the maximum acceleration or the maximum stress, whatever you're interested in. And then you can act accordingly. That's why I said, or not I said, someone else said, that it's true that a theory without an experiment is dry, but an experiment without a theory is blind. And certainly you want to open your eyes on what's going on, and this is published. Then the other problem that we will address is could an impact load of finite duration be substituted by instantaneous impulse? And there's, to a certain extent, the same situation that we have just addressed. Yes, if you run a theoretical analysis, you certainly want to avoid, consider the most general case for loading, whether it's neither static, nor instantaneous impulse, but something in between. You can do that. But the mathematics, even in the case of a linear system, is pretty tedious and complicated. It's called the Duhamel integral. It's done. You can do it. But it's better if once and for all, you do that for a particular system that you're interested in, you do it for particular loading conditions that you're interested in, and then you can substitute that with the instantaneous impulse, provided that you know that the error will be minimal. How minimal is minimal? Yes, that's the question that was answered in this analysis. And on the other hand, if you want to substitute drop tests with shock tests, maybe it's also you can do that. You don't have to mimic the drop conditions directly. You don't have to do that. We know in advance that any accelerated test is a distortion of the real life, and it's okay as long as we know what we are doing, as long as we know how to bridge the gap between what we see during accelerated life testing or accelerated testing and what we'll supposedly get in the field conditions. So could an impact load of finite duration be substituted by an instantaneous impulse? And here I will give an answer based on the linear analysis. We will see later on that the answer on the nonlinear analysis might be quite different. Take a look. What I did here, I simply assumed two types of loading. One, when you have a sinusoidal impulse, which is prescribed by the JEDEC on the left-hand side. It's and on the right-hand side, it's the formulas in the lower row. It's a situation when you have a suddenly applied and suddenly removed load of constant magnitude. So let me show here what I mean. One load is like this, and another load is like this. Yeah, we can say probably that these two areas might be the same. And I examined these cases, and I examined the general case, as I mentioned a minute ago, the most complicated case, but you have to approach this system without applying an additional constraint that it is either a instantaneous impulse, you don't know that in advance, or static. But what I did, I applied instantaneous impulse, and then I examine the situation. What if, because it's clear that this, the area under the curve is an impulse. And so instead of examining a system where the impulse is a sinusoidal, I can examine a system where the impulse is an instantaneous, but its area under the force is the same, the area under the force is the same as this area. And here also, this area. And then they say, and I want to see the difference. If I'll compare this with this, I'll compare this with this, and that means I also indirectly compare this with this. So what will be response, provided that in all the cases, this will be the same area? And here are the results. The results are shown in the table above these two formulas, and chi with 0 below, and as you see here, that's a case when you have a suddenly implied and a suddenly removed load, and the chi with a prime is the second row in the middle, where you have a sinusoidal excitation. And the upper line shows the duration, actual duration of the impulse to the natural period of vibrations. Again, so the upper row, it's a ratio of the load duration to the natural period of vibration. The second law is the error from substituting the actual duration of the impulse, of the instantaneous impulse, in the case of a sine-shaped impact. And the lowest row is the same thing when the impact is due to a suddenly applied and suddenly removed load. And so these chi sub 0, chi sub 1, that's a ratios of the dynamic response to the impact of finite duration to the response to the instantaneous impulse. And as you see here, of course, it should be that if the actual load is an instantaneous impulse, indeed, you have it's 1 in both cases, so no error at all. Then when the duration of the actual load increases, the error increases. But look, it increases not as rapidly as you thought it would. For instance, if the duration of a loading is a quarter of the period of vibrations, let me show here what it actually means. Let's say these are vibrations, and a quarter of a natural, this is a period, and this is a quarter of a period. So if the duration of loading is like this, you see it's quite appreciable duration compared to an instantaneous impulse when it doesn't have any time. So 0.25. In this case, even in this case, you have the error is not significant. It is a little bit higher in the case of a suddenly applied and suddenly removed load. 0.9 is opposite to 1, compared to 1. And for sine-shaped impact is 0.94. So it's only 5%, 6% of an error, and in practical situations is probably acceptable. If you substitute a real short-term impulse in the linear system with a short-term load with an instantaneous impulse. Go ahead and do that, provided that you know that the system is linear. It might be telling you in advance in a nonlinear system, if it's very significant nonlinearity, it's a different ball game, but not necessarily to the worse. Might be to the better, but there are some subtle things that we'll discuss later. So to summarize this part, I want to tell you this. Yes, if you know the duration of loading, first of all, I was a little bit puzzled that I didn't see in the JEDEC specifications indication about how the duration of loading should be related to the natural period of vibrations. They should refer to that. Maybe they will do that, what I heard in the future. But this is a very important thing, because there is no such thing as dynamic loading per se. What is dynamic, it depends on the natural frequency of vibrations, period of vibrations. Again, as I started in the beginning of this course, what's considered static if the durations of loading is significant compared to the duration of the period of vibrations, natural period of vibrations. If it can be treated as another extreme case as instantaneous impulse, if the durations of loading is significantly lower than the natural frequency of vibrations. And what means significantly? Now we know what means significantly. It should be, if it's lower than, let's say, 1/8 of a year period, as you see here, it will be just less than 2% in the case of a sinusoidal impulse, and about 2.5% in the case of a suddenly applied and suddenly removed load. So it means for any other load, it will be pretty much something the same, a couple of percent, who cares? So that means that if the load is duration is smaller than 1/8 of a period, it's absolutely acceptable to substitute the actual shock load with the instantaneous impulse. But even its durations are high as a quarter of a period, it's still possible. By the way, I want to indicate that a quarter of a period has a very important physical meaning. It means that the system needs a quarter of a period of its vibrations to be deflected from the equilibrium position to the maximum displacement, where the maximum amplitudes, the maximum stresses occur. Therefore, a quarter of a period is a very important characteristic of vibrations. By the way, That's another important thing that we will discuss a little later, but in this connection I want to start talking about that right away, is this. Because I've just indicated, we have just mentioned, and we all agreed, that it takes the system a certain time, might be a short period of time, but certain time to get deflected from the moment when it was loaded to the moment when it will exhibit the highest deflections, the highest stresses. It takes time. And this time is a quarter of a period of vibrations. Now, if you have an instantaneous impulse, the maximum force in the instantaneous impulse can be huge. If this force is applied statically, well, yes, it will destroy the system completely. But the good news is that it's not applied statically, it's applied dynamically. And the system simply doesn't have time to react to the maximum value of this force, because the force lasts for only a small period of time, and the system simply doesn't have time to respond. Fine. So it responds not to the maximum value of this force, that, again, if applied statically, would destroy the system, but it responds to the impulse, to the area under the force. And if the force can be, the maximum value of the force can be huge, but if the duration of this force is very, very short, the area will be finite, and it's fine. That's why in other areas of engineering, for instance, in the rapidly shooting artillery, that and this, in a rifle, the statical force can be huge, but because the time during which the load is applied is very short compared to the natural period of vibration, the system is able to withstand that and doesn't react to that. That's a rare case when static loading is more dangerous than dynamic loading. Typically, we are used to a situation if the same load is applied statically, it's probably better than it's applied dynamically. And that's true. Let me show you a situation which is a classical, well-known situation, and we all talk often about the dynamic factor. What dynamic factor means? Dynamic factor means that what is the maximum displacement? What's the maximum stress in the linear system if the same force is applied dynamically rather than statically? Let me show you a typical situation that people often think of, and then I'll go back and tell you the atypical situation with an instantaneous impulse. Why we are saying often that the dynamic factor is bad, it's greater than unity. Even quite often you can find that the dynamic factor is assumed 2. 2 is used here not because 2 is greater than 1 and lower than 3. 2 in this situation has a very clear physical meaning that I'm going to explain. Let's say you have a beam, a plate, a printed circuit board, you have a certain load that is applied to this beam statically. And let's say this displacement will be, let me call it F. If you take the same load and will apply it dynamically, that means we'll suddenly apply to this system and the load will stay on this system. In terms of time, it will be a load like this. Constant load that was applied instantaneously and stayed on the system, and this is time. In this case, if the same load is applied on the system and deflect the system, it could be demonstrated that the amplitude is twice as 2F, twice as high. By the way, in this case, it will vibrate this way and this way. But in this case, when the load stays there, it will vibrate from here, go from here to here. From here to here. But the maximum displacement, it will not be an amplitude because the neutral line will be here, not here anymore, but it will be twice as high. That's why in this situation, when you have a uniformly distributed load, if you have a simply supported beam and that and this, yeah, it's true. But in this case, and this is typical, well-known case, when dynamically applied, the same load is worse, results in higher stresses than static load. But there are also cases when it's just the other way around, when a dynamic loading is less dangerous, less dangerous, less detrimental than a static loaded could be, because the system simply doesn't have time to react. Let's continue. Now I want to talk about compliant interfaces. I said at the beginning of this course that quite often we use compliant attachments in electronic engineering to bring in them as a strain buffer to bring down the thermal induced stresses. This, by the way, now everyone works in the field of three-dimensional packaging, including so-called TSVs, through silica vias. And one of the ways to bring down the stresses in TSVs is to employ compliant attachments between the copper and the silicon. Well-known approach, which is less well-known but also interesting, to what extent these compliant interfaces, which are used in electronics, do their job or are useful, might be useful in terms of dynamic loading. And I had a project with that. You'll see here I mentioned Dr. Vujošević from Intel, that we do a nice analytical work that was published in Journal of Applied Physics, and also experimental work is going on now. And ultimately we want to use it to understand the relief that can be expected in terms of the stresses and strains of behavior of ball grid arrays due to the application of the compliant attachments. Here's a problem that we addressed. Look at this, we call it board intention. Look at this, let's say the lower component is a printed circuit board, the upper component is a package, and in between it could be, let's say, a ball grid array, or could be something else, a hypothetical. The beauty of analytical modeling could be everything. Let's say in between it could be a solder layer, or it could be an adhesive bond, whatever. The thing is that if you, in the drop tests, the printed circuit board is subjected to tension. It's also subjected to bending, but the tension, we already knew that the tension is huge, and the more severe the loading is, the lesser role is played by bending, and the greater role is played by tension. And here, therefore, we examine the situation when you have tension only, which is applied to the lower component. And the question was, how is it transmitted to the upper component? And as a result of that, what type of stresses and strains will be exhibited by the interfacial compliant layer? It's clear that if the compliance of this layer is infinitely high, that means that the layer simply doesn't exist. That means that the upper component will be not stressed at all, and all the force, all the stresses will be experienced by the lower component. On the other hand, in the other extreme, where the interfacial compliant layer is not compliant, but it's ideally stiff, in this case, in the mid portion of a long enough assembly, the stresses, the forces first, will be distributed proportional to the axial stiffnesses of these two components, well known. And at the very ends, the upper component will not exhibit anything, but the lower component will exhibit all the stresses, but in accordance with what mechanical engineers know, Saint-Venant principle. All these effects will go away when we move far away from the ends. So here on these formula at the left-hand side, you see the result for the interfacial shearing stress. The T, capital T with the hat is the external force. K is a parameter of the interfacial shearing stress that depends on the axial compliance of the entire structure and the compliance with respect to shearing forces, primarily of the bonding layer. And A is, you see, is half of the length of the assembly. And that's how you can calculate the shear stress along the interface, the maximum stress and everything. And that's how this shear stress is distributed. The upper figure shows how it's distributed over the length of the assembly. And as you see, it concentrates at the ends, while the mid portion is practically stress-free. And the lower plot shows how this stress, the maximum stress at the end of the assembly, how it depends on the length of the assembly. And what you see here of course, if the length of the assembly is 0, the stress is 0. But if the length of the assembly is here, believe it's 5 millimeters, 10 millimeters, and so on, if the stress is already high, whatever it is, it doesn't increase with a further increase in the length of the assembly, which is in good agreement with the results that I mentioned to you a couple of hours ago, and that were obtained many years ago in my paper published in Journal of Applied Mechanics in application to thermal stresses, but certainly it's also true in application to mechanical loading. In other words, what's true is that the stress, the maximum shearing stress, if it's high enough, and how high is high depends, can be predicted and calculated based on a particular situation. It doesn't go up if the structure is large enough. And again, how large and how high and how that is depends and can be easily calculated. By the way, in application to thermal stresses, I remember that if we will consider a chip which is 10 millimeters or 10 millimeters attached to a substrate with the epoxy about 2 mil thick, so the further increase in the size of such a chip will not result in the increase in stresses, neither normal stresses in the chip itself nor the shearing stress or peeling stresses in the face. And of course, if you want to achieve lower stresses, you can either make the attachment thicker, more compliant, or use smaller chips, which is probably nobody will be using that. But at the same time, I want to indicate that in photonics, we still use chips which are significantly smaller than the chips in electronics. Let's continue. So here that we did that analysis, what you saw on the previous slide, that was shearing stresses. Here we obtained nice, elegant formulas for the peeling stresses. And here you see also the plots for these stresses. The peeling stresses you see on the upper. For the situation, by the way, when the board is subjected to pure bending. We saw, and you see it's published in the Journal of Applied Physics, the peeling stress should be self-equilibrated. In other words, the area above the diagram for the peeling stress and the area below the diagram, these areas should be the same, while the maximum peeling stress at the end is significantly higher than the minimal peeling stress, which is in the cross-section that is a little bit remote from the end. And there are some other interesting things, unpredictable, I would say, based, again, if you know, you can use finite element analysis, but if you don't, use modeling, analytical modeling. Here we applied both techniques and both loadings, and we obtained very interesting results. I will not go through these results, which are not directly associated with dynamic response, but, and this is also when you have a combined action of bending and stretching. And actually, yes, you have this situation when you drop the device. And I will not describe the details. If you're interested, you can take the published article, and it's an interesting interaction of the bending and tensile loading. And here is the combined action of tension and bending for the dynamic response. And that's what we did, because you see, if you look at this test vehicle or experimental setup, it's exactly just upside down what we have just described. You have a printed circuit board, you have a element, surface-mounted device that you are testing, and one is attached to the circuit board. Could be ball grid array, could be compliant attachment of any other type. And also, because we want to know the tensile forces and the bending moments, you can do that if you apply two strain gauges on both sides. And certainly, it will be on the next view graph, you can, if you have the reading of these two gauges, you can calculate both the tensile force and the bending moment. Let me show you. And that's what you see on these two, with these two formulas. In these formulas, if you measured epsilon sub 1 and epsilon sub 2 on the convex and concave parts of the printed circuit board during testing, and then you know the thickness of the board, H, and you know Young's modulus of the board material, E, and you know the Poisson's ratio of the board material. Here's a nu in the nominator. Then you can calculate both the force and the moment. I will go back to the previous view graph, and we'll read it, what it says. And then I'll come back to the next one. The developed stress model was used as an appropriate illustration of the possible use of this model for the evaluation of the dynamic response of printed circuit board and surface-mounted device assembly to impact loading. The loading was applied to the printed circuit board support contour and is transmitted to the surface-mounted device through the attachment of finite compliance. In our experimental study, we used the input information for the forces and moments obtained from the strain gauge data employed in special design experiments. In these experiments, two strain gauges were attached to the printed circuit board in the vicinity of the component, and one strain gauge was placed on the top surface of the board and another on the bottom surface. Let me tell you this, since many of those who will be reading, well, the notes of my course, let me tell you this. Certainly, the bottom line, ultimately, we want to understand the strains that are generated in the vicinity of the solder joints, because it's the corner solder joints that are the most vulnerable ones. Although now people try to make their lives easier by bringing in epoxies at the corners, that and this, but still so far the solder joints, the peripheral solder joints at the corners are the most vulnerable ones. And but on the other hand, at the ends of the corners, or where the printed circuit, where the surface-mounted device is mounted on the board at the corners, there is a significant stress concentration. And at the same time, if we will place our gauges there, they will show God knows what. It will be a combination of actual tensile forces and bending moments, and this will be muddied by the significant level of stress concentration. So my suggestion was we can predict the stress concentration differently, theoretically, for the given force and for the given moment. But first we want to understand how predictable these forces and moments are from the general analytical model, nonlinear model that we have not discussed it yet today. And therefore the gauges should not be placed very close to the corners. I suggest probably a little bit, maybe one thickness of the board remote from the corners. And now let's see. These are the coded strains, and these are how we, on the bottom, its forces and moments are compared at the time of period of time of 12 milliseconds. And you see the plots that are actual experimental plots that we obtained. With this, let me make a break, and we will continue after the break with the rest of the course. Thank you.